Let's discuss final topic of this textbook called the multiple linear regression analysis. It is advanced topic and not easy to calculate by hand. Therefore, we have to rely on the package. Let's consider, we'll discuss a model and then some other validation things. Consider this example. You have three variables measured on maybe 15 tree. Well, it shows diameter, height, volume like that. The motivation is how can we estimate volume based on diameter and height? Okay. Well, there are many ways, but we can think this kind of mathematical model. Let's say this is y variable, and maybe this is x1 variable, x2 variable. Then we try to have some mathematical formula between y and x and x2. One possibility is maybe you may write down y equal beta 0 plus beta 1 x1 plus beta 2 x2. It is exactly extension of a simple linear regression analysis. Therefore, we call multiple linear regression. Let's look at how it look like. Okay, using the actual example. Go to eStat. From the ebook folder, why don't you find this example? It's a 3 volume. Can you see this data? There are 3 variables: diameter, height, volume. Well, we'd like to apply regression analysis. Click this regression icon. The y variable is volume, okay? And x variable, maybe you can click these 2 variables. They're gonna generate the scalar plot matrix like this. Then, if you click regression analysis, well, initially they show you the descriptive statistic of each variable and then some correlation matrix, then regression analysis. It seems they calculate the coefficient about the diameter and height and then some intercept value. It looks like they calculate standard error and test statistic, and then the corresponding p-value. Then they calculated analysis of variance. Let's look at what does that mean. Multiple linear regression analysis in general can be represented in this manner. Okay, you have one response variable and k independent variable. In matrix notation, you may write down this relationship as like this, and then you may have a similar technique as we discussed in simple linear regression called the method of least square method. I mean, graphically, there are some n-dimensional space, k plus 1-dimensional spaces, and we'd like to find some kind of hyperplane which satisfy least square method. It's the same thing as yi minus yi hat. It's try to minimize residual based on our mathematical model. Here's a least square estimator by using the matrix notation, but I don't want to get involved in detail. Why don't you accept this kind of result? Here's also residual standard error S. It is a square root of, this is mean square error again. Well, you can have an analysis of variance like this. I mean, you calculate sum of square due to regression and sum of square due to error. That's a residual error. Then sum of square total, this is yi minus y bar square, means sum. You have a similar expression like this. We calculate corresponding degree of freedom. There are k, the independent variable, and sum of square error is m minus k minus 1. If you add these two, it becomes m minus 1. Mean square of regression and error look like this. And we calculate f value by calculating ratio of mean square regression divided by mean square error. The purpose of this Anova is we are testing all the regression coefficients are equal to 0 or not. What does that mean? Well, our model look like this. We are testing all these coefficients equal 0. That means yi become beta 0 constant, no relationship between yi and xi. That's the purpose of regression analysis. Okay? If this is true, then you don't need to go further. Your model is wrong. Therefore, you are not supposed to use multiple linear regression. But if it is rejected, that means at least one of these beta I is not equal to 0. In order to do that, we do analysis as the simple linear regression. I mean, simply we are testing whether this coefficient equal to 0 or not by using this test statistic. It is complicated calculation. You have to rely on the package. In overall, you do analysis of variance first. If it is rejected, you check which one is beta equal 0 or not. Okay? If all of them is not equal to 0, then you can use all the independent variable on your model. But if some of them is 0, some are not, then erase on your model such that beta I equals 0. If you look at the output, they look like this. I mean, I already showed you. In each coefficient, regression coefficient, they calculate standard error and corresponding test statistic. But before you get into here, you have to look at the Anova. The overall, the objective is we'd like to test that such that H0 is beta 1, beta 2 equals 0. If you look at p-value, you have to reject the null hypothesis. Therefore, at least one of the beta I is not equal to 0. We usually do not testing hypothesis about the beta 0 intercept. We are looking beta 1, beta 2. It seems their p-value is very small. If you are using significance level 5%, they are reject. That means on your original data, the x1 variable, x2 variable are valid in this model. That's the validation procedure. Maybe one more thing is you have to check residual. Remember what was the purpose of residual analysis? You need to check normality. We are using QQ plan. I didn't explain detail. We are just looking whether it is the dot located on the line. Okay, it looks like close to line. Then we are checking the randomness of this residual. It looks like it is a little outlier. You need to check that. Like well, they are random, or in each xi value they scattered evenly. That means we are checking the same variance, homoscedasticity. Okay, you need to check normality, randomness, and then same variance. That's the key factor to do residual analysis. Okay, these are all for multiple linear regression analysis. Thanks for your time to listen my